While sitting under a tree like this, Isaac Newton observed an apple fall to the ground. This was the eureka moment for young Newton that led him to eventually publish a comprehensive theory of something we now call gravity. But gravity had existed before Newton. Scientists before him had figured out that no matter the mass of objects, they would all accelerate towards the Earth at the same rate. Through reasoning, Newton derived his law of gravitation. He said that the force due to gravity is equal to the mass of the first object times the mass of the second object divided by the distance between the objects squared times the universal gravitation constant, which is roughly 6.67 times 10 to the negative 11th. But how did Newton find the mass of objects like the Earth and the Sun? In 1609, Johannes Kepler published discoveries stating that satellites always travel in elliptical orbits. This means that planets and other celestial satellites follow circular motion principles. We know that objects in circular motion experience a centripetal acceleration, which is equal to the velocity of the object squared over the radius of the orbit. Newton's radical theory was that gravity caused the centripetal acceleration in orbits. Newton brought these ideas together using his second law of motion, force equals mass times acceleration. By substituting Newton's law of gravitation and centripetal acceleration in a little algebra, we can find that the velocity of the orbiting body squared is equal to the gravitation constant times the mass divided by the radius of the orbit. Going a little further, since we know that the velocity equals distance divided by time, and in this case the circumference of the orbit divided by the time, we can say that 2 pi times the radius of the orbit divided by the time squared is equal to the gravitation constant times the mass of the object divided by the radius of the orbit. When we simplify through algebra, we are left with this equation. Through this equation, we get what is known as Kepler's third law. At its core, it states that t squared is proportional to r cubed, or that the orbital period of a satellite squared is equal to the radius of its orbit cubed. In the late 17th century, this was a groundbreaking revelation. By just observing planetary motion and using this equation, scientists like Newton were able to measure the mass of the Sun, the distance between the Earth and the Moon, and even the mass of stars light years away. An apple falling in Newton's orchard unlocked a way for scientists to be able to measure the fundamental properties of our solar system and galaxies far away.